Okay, so we are going to do an example of Snell's law. And here's our example. We have a piece of thin glass with parallel sides, so kind of like a window pane. And we have an incident ray of light hitting that glass with an angle of incidence of 60 degrees. So I'm going to indicate that it is coming from air, so we're in air. This is a pane of glass, and then it goes back through the glass back to air. And so my question is, what is the angle of refraction in the glass? And then what is the angle of refraction as it returns to the air? Now, Snell's law tells us that the index of refraction times the sine of the angle of incidence for one material is equal to the index of refraction times the angle of refraction into that other material. So we're going to use Snell's law to solve this problem. Of course, we need to know the index of refraction for both air and glass. So the index of refraction for air, we're going to assume a vacuum in this case is 1, and normal air typically has, not too humid air, has that index of refraction. And the index of refraction for glass is 1.5. Okay, so part A is going from air to glass. So our incident ray is going to be air. Our refracted ray is going to be in the glass. So we have the index of refraction of air times the sine of the incident angle in air is going to equal the index of refraction of glass times the sine of the refracted angle in glass. So I'm going to use I as incident, R as refracted. I think I said incident, but whatever. I is incidence and moving forward. And then the A is representing air and G is representing glass. Okay, so and we can solve. We're trying to find the angle of refraction in the glass. So I'm going to solve for the sine of the angle of refraction in the glass, and we get the angle of, the index of refraction in air divided by the index of refraction in glass times the sine of the incident ray in air is going to give me the sine of the refracted ray in glass. So we can plug in our numbers. We have 1.0 over 1.5 times the sine. Now, what is the incident angle? Well, we are told that it is 60 degrees. So times the sine of 60 is going to equal the sine of the angle, the refracted angle in glass. And this comes out to be 0.866 is equal to the sine, nope, not 0.866, sorry. Wrong one. This is 0.5774 is equal to my sine of the refracted ray in glass. And if I take the inverse sine, we get an angle of 35.3 degrees. So our angle of refraction in glass is 35.3 degrees. So I'm going to put angle of refraction in the glass is equal to 35.3 degrees. All right, so using Snell's law to determine that. Now, we're also interested in looking at another example of using Snell's law. What will be the refracted angle back out to the air? Well, since the two sides are parallel and light travels in a straight line through a medium, using our geometry, we know that if the light ray in the glass is refracted and now has a refracted angle of 35.3 degrees, that refracted angle in the glass is equal to the incident angle in the glass as it exits. So now the glass, the light ray in the glass becomes our incident ray, and those angles are the same. So using Snell's law, if we consider this left side of the equation the incident equation, now we are dealing with the index of refraction in glass times the sine of the incident ray in the glass is equal to the index of refraction in air times the sine of the angle for the refracted angle in air, okay? And this is what we're interested in solving for. So I'm going to solve for that. I have the index of refraction in glass divided by the index of refraction in air times the sine of the incident ray in glass is going to equal the sine of the refracted ray in air. And now we'll put in our numbers. Glass is 1.50, air is 1, times the sine. Now this is where that geometry helps us out. So the incident ray in glass is equivalent to what that refracted ray was into the glass, since it travels in a straight line. So that's 35.3 degrees. And that's going to equal the sine of our incident ray, or our refracted ray in air. And so if I do that math, that is my 0.866 is equal to the sine of the refracted ray in air. And that gives us, if I take the inverse sine, an angle, of 60 degrees. Well, now isn't that interesting? 60 degrees was, of course, my incident ray to start this problem. What does that tell us? That tells us that a ray of light going from air to glass back to air doesn't actually change its angle. Now, interestingly, it does change its position slightly. So we can imagine if I just draw my vertical here, as it comes in, it's going from a low to a high, so it's towards the normal. That 35.3 degrees tells us that. So let's say it's about like this, and then it goes back out at that 60 degrees. So the ray remains at the same angle relative to the glass, but it's slightly shifted. Okay, so it's just shifted ever so slightly. So where do we notice this? Well, we actually don't notice that the object is shifted if I look through a pane of glass. Everything looks kind of normal. There's no distortion, right? But if I go really close to the edge of that pane of glass and I kind of go between the air to the glass, you will see a slight jump. So anyway, fun little fact there, but using Snell's law to get us those angles. Good job.